At this point, we've talked about the unit circle and just circles in general. We've defined these things called the trig functions, in particular sine, cosine, and tangent. And we've talked about similar triangles and why this is a well-defined thing. We're going to step back and basically redo some of that and talk about what these things mean in terms of triangles. And this is what we refer to as right triangle trig. So the idea is this. We start with our regular definition here, and I'm going to assume that we have a circle of some radius r. And then we're going to play a familiar game of find the triangle. And the idea is this. If I take my point and I draw a straight line down to the horizontal axis, I've just defined a triangle. Okay? So if I look at this triangle, it's a right triangle there, that's the key thing. That triangle actually looks like that. And because I know this coordinate has a horizontal component of x and a vertical component of y, that distance is x and that distance is y. And notice, if we keep these same definitions, we have that the sine of this angle is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and the tangent is going to be the opposite side divided by the length of the adjacent side. Okay, and that's the old familiar SOHCAHTOA that you've probably heard before. Okay? So the way we were talking about these trig functions in terms of the unit circle is no different than what you've previously done with right triangles. Okay? So everything here is consistent. And the reason it's consistent is because there's this hidden right triangle inside of here. So we're going to talk about different ways to look at this and what are the results from some of this. So the first thing to notice is because this is a right triangle, I know that the Pythagorean identity is going to work out here. So x, y, and r have to satisfy this. But notice, if I divide both sides by r squared, okay, what do I get? I'm going to multiply this through on the left. I have x squared over r squared. I pull that over, I get y squared over r squared. R squared divided by r squared is just 1. And I'm assuming r is not 0 here. Let me rewrite this. I can think of this as, instead of x squared over r squared, I can think of this as x over r squared. I'm going to do the same thing here. This is y over r quantity squared is equal to 1. And now notice x over r is cosine. So this is the cosine of theta squared. Y over r is sine. So I get cosine squared plus sine squared equals 1. Okay? This is oftentimes referred to as the Pythagorean identity, and what happens is this means that sine and cosine are explicitly tied together. Okay? Now this identity by itself also leads to other forms. So let's come back up to here. Actually, let me start back up with this. So this decision to divide through by the r squared was an arbitrary choice. Okay? Let me do this. Let me divide through by x squared. I can do this. So here's what I'm going to do. I'm going to divide through by x squared on everything, like so. And if I multiply this through, this times this, I get 1 over x squared times x squared. This is going to be y squared divided by x squared. Let me just leave this as r squared over x squared. All right, so let's assume that x is not 0 for this one. And we just leave it right at that. So this becomes 1. This is 1 over y over x quantity squared. This is r over x quantity squared. But notice, what's y over x? Y over x is the tangent. So I get 1 plus the tangent squared. Oops, I screwed up. That should be an equal sign. Sorry. Now, what r over x? Now notice here, I've got an x over r, and so this, I can think of this as 1 over x over r. So that's the same thing. So I just take 1 over that. So I get this, and this thing is 1 over cosine squared. Okay. Now, this kind of relationship pops up enough that we're going to give it its own name. And what we're going to do is we're going to extend these things, we're going to give these new names. If I flip this, if I look at r over y, I'm going to call that the cosecant. If I flip this, I get r over x, so we get 1 over cosine. Sorry. I'm going to call that the secant of theta, and if I flip this, I get x over y. I'm going to call that the cotangent. And all of this implies that this is what? 1 over sine, as long as sine is not 0. This is 1 over cosine, as long as cosine is not 0, excuse me. And that's 1 over tangent, as long as tangent is not 0. So what does this mean? That means this relationship here is going to be 1 plus tangent squared is secant squared. And if I come back, this was confusing how I did this. Notice I have r over x squared. There's my r over x, and there's my secant squared. Okay? So this thing is exactly coming from that. Okay? All right. Now, how do we use this? I'm going to be a little bit careful here. Before I give an example of how we might use this, I'm going to define some terms. And the reason I need to define these terms is when we try to describe a physical situation, it can be really confusing to talk about which angle is which. So we've got a couple terms here that make this a lot easier. So the idea is, suppose you are looking straight ahead on the horizontal. So there's your eye looking straight ahead. Okay. If you rotate your eye up some angle, so if you go upwards, like so, and you're looking at some bird above the horizontal, we're going to have an angle there. This is called the angle of elevation. Okay. If, on the other hand, suppose you are looking straight along the horizontal and you rotate your eye downwards, so like this, and suppose you're looking at some fish, then this is called the angle of depression. Okay? And this definition will make it much easier to describe what's going on. We're going to make heavy use of this. And the reason is it just it makes things less ambiguous about what angle you're talking about. So now let's look at an example. Okay. So be careful here. Some vultures sitting on a tree limb. Oops, a period. Okay, it's 8 meters above the ground. Looks downwards and sees a rabbit. Okay, so it sees a rabbit that's not dead. The rabbit's on the ground. and the angle of depression is 12 degrees. So because I said angle of depression, I know that it's looking downward. I want to know how far away is the rabbit. Okay. So let's see, let's go through our steps. First step is read this. So let's see, we don't really care what this thing is or where it's at. But we do care that it's 8 meters above the ground. Okay. And it has an angle of depression of 12 degrees. And we want to know how far away is it. So here's the actual question, and here's the given information. So given that information, what does that imply about this? Now we have to be a little careful. There's different ways to interpret this. So I'm going to try to make it clear how I'm interpreting this. And if I get it wrong, at least I can get some partial credit out of it. Okay. So let's see. My next step is to draw a picture. So the idea is I've got my vulture here, and I've got my bunny rabbit here, and it's looking down here, and it has an angle of depression of 12 degrees. Okay. And the question is, can I find a triangle here? If I can find a triangle, then I can start relating angles and distances using some of the trig functions. Now there's a couple different triangles here, and I'm going to use this one to work with. Okay, so there's the hidden triangle. And once I get this, everything else is hopefully going to fall into place. So now let's see. Next step. Now no variables have actually been given to me, so I've got to define them, and I've got to make it clear what I'm using here. So I'm going to call this, I'm going to use a different color here. I'm going to interpret this, the hypotenuse of this triangle, to be the distance away. Some people may think it's the horizontal distance, and that's an okay interpretation, but I have to make it clear. So I'm going to define my distance to be the length of this hypotenuse. This side of the triangle, I'm going to call that the horizontal distance, and I'm going to define that to be x. And this distance here, I'm going to define that to be my vertical distance. Okay? All right. And so I've got my angle is given to me there. Okay? So I've defined my variables. I've got my distance I'll call r, vertical distance I'll call y, and my horizontal distance I will call x. And now I've got to figure out what are the relationships that I have between these things. Now, here's the thing, is I want this. I know that y is 8 meters. It's a big tree. And let's see, I don't know r. But I know that theta is 12 degrees. So I could look at the tangent, y divided by x. I could look at the cosine, x divided by r. I could look at the sine, y divided by r for this angle. I want to know r, I know y, so those are the two distances that I should consider. I want to know which trig relationship involves y and r. And this is going to be opposite over hypotenuse. So the sine of that angle is going to be y over r, and when I just said that, that's going to be 8 over r. So there's the main relationship that I'm going to use. Okay? So this is the relationship that ties together the things I know and the things I'm looking for. Okay. All right, my next step is to make a plan. And again, these don't have to be elaborate plans, just a general idea. So the general idea here is I'm going to take this equation and I'm going to solve it for r. So I'm going to do all the algebra steps. And the first thing to notice here is that sine of 12 degrees is just some number. Okay, that's just some number that I need to solve for. And so my next step is to carry through my plan. So let's see, so what do I have? I've got, let me rewrite this. Sine of 12 degrees is 8 over r. I want to get, this is in the denominator, so I want to get all the r's on one side in the numerator. So I'm going to multiply both sides by r. If I do that, I'm going to get r times sine of 12 degrees. Now 8 divided by r times r, the r's are going to cancel, I get that. Now I'm going to divide both sides by that. And I get that number, okay? And now the last step is basically go through and check the work. I will let you do that in a matter of time, but notice I need to go back through, make sure I understand what this means, and if this is correct, that this is the right relationship and the algebra was right. So checking your work means a lot of things. And it means taking a look at this number and asking, does it make sense? So for example here, if this distance is 8, this distance right here should be a lot bigger than that. So when I go through and plug this in a number, or sorry, plug this in a calculator, I should expect to get something much bigger than 8. I don't know, should it be 16? I'm not sure, but I have to ask, does that number make sense? Last thing, I'm going to come back to this picture, and I'm going to ask, what if I had chosen a different triangle? So there's nothing sacred about that choice. Because there's at least one other triangle here. So if I had this is my R. Instead of going this way first, I could have come down that way first, and like that. Okay? And if I'd done that, this is still R. This vertical distance is still Y, and the horizontal distance is still X. What's going to make this different, though, is that angle is now on the outside. Okay? What does that mean? That means then that this angle, this plus this, so theta plus 12 degrees has to be a right angle, or 90 degrees. So if I subtract that from both sides, that's going to give me what, 78 degrees, I hope? Yep. And so now this would be 78 degrees. This, again, is a right triangle, or sorry, right angle. And that means if this is 78 degrees, that has to be 12 degrees, because this plus this has to be 180. And what was the relationship I used before? I had that sine of 12 degrees is y over r. Notice, if I'm still using that angle, or if I hadn't bothered to calculate that, if I do the cosine of that angle, the adjacent is going to be y, and the hypotenuse is r. And I would have gotten something that these have to be the same thing. This says that the sine of 12 degrees has to be equal to the cosine of 78 degrees. And that's basically because of this triangle here, the sine of that angle has to be the cosine of that angle, because the opposite for that is y, and the adjacent for that is also y. Okay? So just notice that there's different ways to do this. It's going to look like you've got different things, but they're all exactly the same, and they're all perfectly fine ways to do things. All right? Thank you.